that's why it's good that mathematicians have OCD sometimes, because we can solve this problem.
Hello, Dr. Peyam.
Hi, how are you? So by the time you watch this video, I'll already be 30. So my birthday is September 29th.
Woo!
Woo! Happy birthday to me.
Happy birthday!
Woo! and for this, I want to present you an integral that seems very boring, but just wait for it in the end, because in the end there'll be an unbelievable consequence. So it's a boring integral with an unbelievable consequence. And I didn't even tell Steve what the consequence is, because I want to know his reaction.
I just know this is your birthday special.
It is my birthday special, so...
Alright, cool.
Okay. And basically, and also, by the way, this is not my idea. I found this idea on Google, and it's by Tom Apostol. This is a mathematician,
Oh, I
he
know
wrote
who
this
he is.
great calculus textbook.
Yes, I know who he is.
And he found, like, the consequence.
Okay.
Okay. But it's still exciting on its own, because it illustrates also a very unusual change of variables. So let's calculate this integral. Let's call it I. Okay. So step one, what we want to do is we want to use a very unusual change of variables. And the reason it's unusual is because it'll turn this integral into another one that's much harder to solve. But it turns out it'll actually be easier to solve. So it's very paradoxical. So let u be x plus y over 2 and v x minus y over 2. Then let's calculate the Jacobian first of all. So du dv, that's, remember, absolute value of the determinant of du dx, du dy, dv dx, dv dy, dv d, okay? So we get absolute value of determinant of, if you want, 1/2, 1/2, sorry, this is a minus 1/2 minus 1/2. Okay. So you get 1/2 times 1 minus 1/2. So 1/4 minus 1/4. So minus 1/2, and you take the absolute value, and you have, if you like, 1/2. I forgot to write dx dy. I know, I'm so bad with my differential. I'm sorry. Okay, that's the first thing, is calculate the differentials. Second of all, we need to figure out what happens to the unit square. What happens to this square? 0, 0, 1, 0, 1, 1, and 0, 1. What happens to this with the new change of variables? xy, well, it'll turn out to be a different figure. But let's see. So what is uv of 0, 0? Well, if x and y are 0, then this becomes 0 and 0. So 0, 0. So this point gets mapped to this point. Okay, and this is u and v. What is uv of 1, 0? Well, you know, this becomes 1 plus 0 over 2, so 1/2, and then, you know, 1 minus 0 over 2, 1/2, so we get the point 1/2, 1/2. So that's good. This point gets mapped to the point 1/2, 1/2. And similarly, if you calculate this, uv of 1, 1, that's 1, 0. So this point gets mapped to this point, 1, 0. And last but not least, uv of 0, 1. That's 1/2 minus 1/2. Okay, so this point here. Okay. So in other words, the square here becomes this following diamond, and I have no idea why anyone would ever come with this idea to turn the square into a diamond, you know. except Rihanna, right? Shine bright like a diamond, right? Okay, but in other words, so some ridiculous idea is to turn the nice square into a diamond, and not only that, we will turn this function into a more complicated function, because if u, remember, if u is x plus y over 2, and v is x minus y over 2, if you actually add both of those up, you get u plus v is x over 2 plus x over 2. Like maybe this x over 2 plus y over 2 plus x over 2 minus y over 2. That's x. So in other words, x becomes u plus v. And similarly, if you do u minus v, that's x over 2 plus y over 2 minus x over 2 plus y over 2. Again, this cancels out, and you get y. So y is u minus v. So our integral, in the end, becomes, in the new variables, it becomes the integral over the diamond D of 1 minus, so 1 minus u plus v, u minus v, and don't forget about the differential. So dx dy is, so remember, du dv is 1/2 dx dy, so dx dy equals to 2 du dv. So we get 2 du dv here. So we took this very nice integral and changed it into this very ugly integral. And as I said, it seems that we're doing stuff that's more complicated, but it turns out this will actually make us solve the integral. You can first of all expand this out. 2 times integral b of 1 minus. So you know, this is a plus b times a minus b, so it's 1 minus u squared plus v squared du dv. But one thing you notice, this is actually an even function in u and v. So it turns out that we can actually simplify this a little bit more. Equals 2 times double integral over d of 1 over 1 minus u squared plus v squared du dv over this region. Right? 0, 0, 1/2, 1/2, 1, 0, and then 1/2 minus 1/2, and that's u, and that's v. This thing. Okay, now notice, this function, as I said, it's even, so it's symmetric across the u-axis, for example. It's also symmetric across the v-axis. So the point is, the total integral over d is actually just equal to 2 times the integral over this upper triangle. Because by evenness, the integral over here is equal to the integral over here. So it's really equal to 2 times integral over this upper triangle. So 2 times 2 times, so 4 times the integral of 1 minus u squared plus v squared du dv, so by evenness. And moreover, the upper triangle, we can split it up into 2 other parts. Namely, again, here's a nice enlarged picture of that triangle. And that's 0, 0. And that's 1, 0. 1/2, 1/2. And 1/2, 0. And the reason we're doing this is because we actually want to calculate that integral. But those 2 regions are very easy to split up. Because if you remember, in the uv plane, this is the line v equals to u. Because it connects the point 0, 0 and 1/2, 1/2. And this is the line v equals to 1 minus u. Because it slopes downwards with a slope of minus 1. So the point is, this integral, if you actually calculate it, it becomes 4 times the integral from 0 to 1/2. Because here we're going from 0 to 1/2 for u, and v is between 0 and u. So 0u, 1 over 1 minus u squared plus v squared, dv du plus, sorry about this, then u goes between 1/2 and 1, and then v is between 0 and 1 minus u of 1 minus u squared plus v squared dv du. So we took the complicated integral, split it up into two horrible integrals, and now, again, let's roll up our math sleeves and let's calculate those two pieces. So let's spend 10 minutes on this integral and like 8 minutes on this integral, and let's calculate them. Again, I've lived for 30 years. I can survive another 10 minutes of this, right? Okay. So.
Oh, by the way, leave a comment down below to take a guess. Who do you guys think who's older?
On the comments, guess who's older, me or black pen, red pen? Alright, so now step 2. And the thing is, here's the idea. In this inner integral, u is constant. So this looks like integral 1 over junk plus v squared. Right. This is like integral 1 over junk squared plus v squared dv. Well, it looks a bit like arctangent. So we want to sort of turn this integral into an arctangent integral. And for this, let's just factor out, 1 minus u squared. So integral from 0 to 1, integral from 0 to u. You factor 1 minus u squared, and you get this times 1 plus, if you want, v squared over 1 minus u squared dv du, and then let's write that down as a square root. First of all, this is independent of v, so you can put this junk here, 1 over 1 minus u squared, integral from 0 to u, 1 over 1 plus v over square root of 1 minus u squared squared dv du. Oh yeah, I know. Life is complicated, so But again, this looks slightly friendlier because we can integrate this. So let's just use a quick change of variables. So let w be v over square root of 1 minus u squared, then dw equals to dv over square root of 1 minus u squared. The point is a then becomes 4 times integral from 0 to 1, 1 minus u squared. So if v is 0, this becomes 0. If v is u, this becomes u over square root of 1 minus u squared. Believe in yourself, okay? So, and then we get 1 over 1 plus w squared, but then there's this junk coming out here. dv is square root of 1 minus u squared dw. So we have the square root of 1 minus u squared dw du. This is not bad, because this comes out here, and it actually cancels out sort of with this one. So in the end, we get integral from 0 to 1 of, again, square root of x over x. That's just 1 over square root of x. Square root of 1 minus u squared. And then, so this integral, without the this part, well, that's just, the antiderivative is just arctangent. So this becomes arctangent of u over square root of 1 minus u squared minus arctangent of 0. So you get arctangent of u over square root of 1 minus u squared du. Holy crap! He's like, what have we done? We took this nice integral and we turned it not only into a square root, but into an arctangent. Like, oh my god, it could not get any worse, but again, believe in yourself. So that's why it's good that mathematicians have OCD sometimes, because we can solve this problem, okay? Alright. it turns out, as ugly as this looks, this actually simplifies quite nicely, because here's a fact. I forgot to say, if you calculate this whole integral, you've basically mastered calculus, because it just puts out every technique you can. Turns out, arctangent of u over square root of 1 minus u squared is actually equal to arcsine of u. Why? Because let theta, it's this cute triangle trick, let theta be arctangent of u over this monster, then tangent of theta equals to u over square root of 1 minus u squared. Now, let's draw a very nice triangle with this property. Well, abracadabra sokatoa. So tangent is opposite over adjacent. So this triangle satisfies a tangent of theta is u over the square root of this chunk. And then if you calculate the hypotenuse, it's square root of u squared plus 1 minus u squared. So in fact, the hypotenuse will become 1. I haven't said this word in a long time. Hypotenuse. Cool. It's like the hypothesis of geometry or something. Okay, so I'm getting 30. Okay. So but then let's calculate what is sine of that junk. Okay. Well, sine of theta becomes opposite over hypotenuse, so u over 1. That's u. So sine of theta equals to u, but what does that mean? Theta is arcsine of u. That's great, because theta was arctangent of this. And so arctangent of this equals to arcsine of this.
Mm-hmm.
So this simplifies. Good. Yay, in case you're still watching, Let me tell you a little story. I was sleeping 2 days ago, and suddenly I felt something very fluffy on my bed. It turned out Oreo was just hopping on my bed at 4 a.m.
Wow.
Very cute. At 4 a.m. though. Okay, where were we? Okay, A, yes. Okay, we're back at A. Remember, there's a B part. Okay, so 4 times integral from 0 to 1, 1 over square root of 1 minus u squared, arcsine of u du. But look, this is very good news, because if you remember, arcsine of, the derivative of arcsine is precisely this. So let's just use a change of variables again. Let's let w be arcsine of u, then dw is precisely this thing, 1 over square root of 1 minus u squared du, which is exactly what you want here. So the point is, this becomes 4 times integral of arcsine of 0 to arcsine of 1 of w dw. But what is arcsine of 1? It's the easy angle that makes sine of theta equals to 1. So pi over 2. And arcsine of 0 is 0. So in the end, you get integral from 0 to pi over 2 of w dw. It's much nicer. Okay. So it becomes 4 times. So pi squared over 4 squared. And that's 1/2. It is. Okay. Oh, wait. Oh, God, no.
Yes, pi square of 8.
I know. I forgot that this is all 1/2.
Ah.
Oh, no. I'm so sorry. I'm really sorry. I realized I made a small typo. I don't know why I put the integral to be from 0 to 1. It's supposed to be from 0 to 1/2. Everything else is valid. So, in fact, and the reason is because, remember, in our region, in this first region A, we're integrating u is from 0 to 1/2. That's how we get 0 to 1/2. But, okay, so arcsine of 1/2, Well, it's an easy angle which makes sine equals to 1/2, so 30 degrees, right? Like pi over 6 radians. This is a 30th special. Okay, so in the end, sorry about that, we get pi squared over 6 squared, and in the end we get pi squared over 18. Okay, we are done with A. We still need to do B, and we still need to figure out why I'm not wasting your time. The good news is it's very similar, so I'm just skipping a couple of steps. So B, well, it's exactly the same trick as before, where you factor out 1 minus u squared. You do the substitution, and you get an arctangent term. So if you do that, square root of 1 minus u squared du. And again, this is very horrible, but we will show it becomes simplified, and I apologize, I wish I could give you a simple intuition why it's become simplified, but it's a little bit of magic. So let's just play around with this a little bit. So let theta, so what do I want to show? I want to show that this arctangent gets simplified, so let theta be arctangent of 1 minus u over square root of 1 minus u squared. Then, tangent of theta becomes 1 minus u over square root of 1 minus u squared. And usually you draw the nice triangle. It turns out there isn't such a nice triangle in this case, but we still have nice identities involving tangent. So let's square this, for example, to get rid of the square root. So tangent squared of theta, that becomes, 1 minus u squared over 1 minus u squared. Important to put the parentheses in the right place, but that becomes 1 minus u times 1 minus u times 1 minus u, 1 plus u. That's 1 minus u over 1 plus u. Okay, tangent squared equals to this sort of nice expression, but tangent squared, remember, that's secant squared minus 1 minus 1. That's 1 minus u over 1 plus u, so secant squared. That's, so, 1 minus u over 1 plus u plus 1, so 1 minus u plus 1 plus u over 1 plus u. Today is all about u, so my viewers, okay, so lots of u's. So we get secant squared is 2 over 1 plus u, and so let's just take the reciprocal of this. Well, secant squared is 1 minus 1 over cosine squared, so cosine squared, that equals to, 1 plus u over 2. So 2 cosine squared equals to 1 plus u. And then there's a nice little simplification. And again, remember what's our goal? It's finding theta. So not delta, but theta this time. Finding Nemo 2, the polar version of Nemo. Then we get 2 cosine theta squared theta minus 1 equals to u. But look, this is actually a nice identity from pre-calculus. This equals to cosine of 2 theta. And this, look how much nicer this looks compared to this, right? So what do we have? 2 theta equals to arc cosine of u. Okay. This apostle is a very smart guy, because I would never have thought of that. So theta is 1/2 arc cosine of u, but it turns out this should be sufficient for our purposes, but let's just simplify this a little bit more, because we like our arc sines. What I want to say is arc cosine is 1/2 times pi over 2 minus arc sine of u, and the reason is if alpha be arcsine of u, then construct a nice triangle with sine of alpha equals to u. Okay. So for example here, SOHCAHTOA, u and 1, well, but u is also equal to cosine of this angle. Cosine of beta, but what is beta? Is pi over 2 minus alpha. Minus alpha, so what do we have? U is cosine of pi over 2 minus alpha, so pi over 2 minus alpha is our cosine of u, so alpha is pi over 2 minus our cosine of u, but remember what is alpha is arcsine of u. Is pi over 2 minus our cosine of u. So this talk is great because we prove lots of identities we'll never need later, you know? But it's still good to know. Okay, so where were we? We basically showed that arctangent of 1 minus u over this square root stuff equals to this thing, 1/2 times pi over 2 minus arcsine of u. I promise you, well, no, we're not almost done, but we're good. This was, I think, the hardest part. So we showed that arctangent of this jump equals to 1/2 times pi over 2 minus arcsine of u. That's pi over 4. So what does that tell us? It tells us that our integral d, so from a long time ago, like this one, 4 times 1/2 times 1 over square root of 1 minus u squared. Arctangent of 1 minus u over square root of 1 minus u squared du. I promise you it'll be worth of your time, because you'll see that the consequence is just 1 over square root of 1 minus u squared. I mean, there's a reason I'm, playing my birthday sort of on this. Right? So we get this integral, okay, which we can simplify if you want. Pi, integral from 1/2 to 1/2 of 1 over square root of 1 minus u squared du minus 2 times integral 1/2 to 1/2 of arcsine of u over square root of 1 minus u squared. Okay, du. Here, you got your du, okay? Look, the first integral here, it involves square roots, but we know an antiderivative is arcsine, so it's pi times arcsine of 1 minus arcsine of 1/2. Well, and for this integral, if you want, you can just let w, just like with before, w be arcsine of u, and you change variables, and you get, just like before, that we get 1/2 arcsine of 1 squared minus 1/2 arcsine of 1/2 squared. And all this junk we can calculate, so it's pi times an easy angle whose sine is 1 is pi over 2. An easy angle whose sine is 1/2 is pi over 6. And then you just do the same thing. So first of all, the 2's here cancel out, etc., etc. So minus pi squared over 4 minus pi squared over 36. Pi over 2 squared, pi over 6 squared. And if you calculate this junk, over 2 minus pi squared over 6 minus pi squared over 4 plus pi squared over 36. You get pi squared over 9. Okay, good. we calculated A, we calculated B, so our integral, in the end, it equals A plus B, okay, which is pi squared over 18 plus pi squared over 9. Fortunately, it's not pi squared over 30, but it's okay. And we get, in the end, pi squared over 6. I know, but don't. You may have figured it out now, but let me now show you why this integral is exciting. Survived our vegetables and everything, now we have delicious birthday cake. Because here's our grand finale. So step 4. Remember what we had? I, so pi squared over 6, that's I, that's integral from 0 to 1, integral from 0 to 1, of 1 over 1 minus xy, dx dy. We calculated this, but look, 1 over 1 minus z, and especially x and y are between 0 and 1, so their product is between 0 and 1, this is actually just a geometric series. So 1 plus z squared, blah, blah, blah. So the inside junk, if you want, is integral from 0 to 1, integral from 0 to 1, sum from n equals to 0 to infinity of xy to the m dx dy. So it's 1, if you want this, what I'm saying is this, 1 over 1 minus xy is 1, plus xy, plus xy squared, blah, 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 blah. Okay, here I'm not very rigorous, but because x and y is between 0 and 1, and things are smooth, let's just assume that we can just take the sum outside of the integral. Integral from 0 to 1, integral from 0 to 1, and we get x to the m, y to the m, dx dy. But look, this is entirely separable. So for example, we can take this y outside of the first integral, and we get that in the end we get the following two integrals. Sum m equals to 0 to infinity, integral from 0 to 1 of x to the m dx, integral to 0 to 1 y to the m dy, Peyam, okay? And again, if you want, you can justify this by just putting this inside of this integral. But look, this is much easier to evaluate than the other integrals. It's just a 1D integral. This equals to sum from m equals to 0 to infinity. So antiderivative is x to the m plus 1 over m plus 1. So from 0 to 1. So 1 over m plus 1 and 1 over m plus 1. Well, but that's just sum from m equals to 0 to infinity of 1 over m plus 1 squared. But what is this? It's just 1 plus 1 squared. Sorry, 1 plus 1 over 2 squared plus 1 over 3 squared, blah, 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 blah. So in other words, if you just let n to be m plus 1, n goes from 1 to infinity of 1 over n squared. So let's just go back. We've actually shown that sum from n from 1 to infinity of 1 over n squared is pi squared over 6.
Wow!
Yay, happy birthday to me!
Wow! Woo! Well, this is like another proof, right?
Yeah, but just using calculus.
Yeah.
Yeah.
Integrals, actually.
So it's not easy, but it's elementary. Because it just uses the hardest thing we've used are Jacobians.
Right. Yeah. Calculus 3. That's all. Yeah. Nice. Woo!
Ta-da!
Nice.
Maya hoo, Maya ho, Maya ha, Maya hee, Maya hoo, Maya ho, Maya ha.